A very good morning to all the students. I am Dr. HimaBindhu from the Department of Mechanical Engineering, and I'm here to teach you the robotics subject. And today's topic is Denavit and Hartenberg parameter, which you also call it as DH parameter. What is the use of these DH parameters? How do you solve the matrix for these DH parameters? Related applications will be seen in today's section. Firstly, what is DH parameter? What do you mean by Denavit and Hartenberg parameter? In 1955, in the year 1955, a scientist called Denavit and Hartenberg have introduced the matrix in order to find out the position and orientation of the robot's manipulator, right? Based upon the different links, based upon the different joints, and based upon the end effector position, they have determined the matrix in order to find out the position and orientation of the robot's manipulator. So, based on their names, that is Denavit and Hartenberg, this particular parameter was being called as DH parameter. Right? Based on their names, it was being termed as DH parameter. Why is this particular DH parameter used? What is the use of this particular DH parameter? It is used to describe the kinematic properties of the links and joints of the robot. Right? The Denavit and Hartenberg parameter is used to find out the properties, kinematic properties, using the links and joints of the robot, where the values are directly affecting the position and orientation of the end effector. Right? It is based upon the kinematic properties of the links and joints, we can find out the end effector's position or orientation of any particular robot. Right? Now, this particular DH parameter is generally used to define the geometry of how each of the rigid body attached to its joint. That is, each of the rigid body, how it is attached to. You can see this figure here, right? So, how this particular body is attached to with each other with the help of the joint will be defined using this DH parameter, and it is also used to calculate the kinematics and dynamics of the robot. It is also the DH parameter is also used to find out the kinematic and dynamics of the robot, dynamic movement of the robot, with the help of which only we can find out the orientation and position of the robot's manipulator. Now, not only that, this particular DH parameter are often used in robotics in order to describe the properties like axis orientation. Axis means the center line, whatever we are getting, right? In order to find out the axis orientation, or in order to find out the arm length, that is from one joint to the other joint, what is the arm length, right? Or what is the shortened DH parameter which we acquire for the robot will be determined with the help of the DH parameter, right? So, what is a DH parameter? What it's used? It is used to find out the orientation and position of the M effector with the help of the links and joints of the robot. And it is also used to define the rigidity of the robot's joints or geometry of the robot's joint. And it is used to calculate the kinematics and dynamic motion of the robot. And it is also used to find out the properties of the axis of the orientation and also the arm length of the robot. Clear? Now, based on these particular parameters, we will be finding out how we solve the matrix for this particular DH parameter. Now, you can see this figure, right? So, here this is the joint 1, right? This is the joint 1, this is the joint 2, and this is the end effector, right? And this is the end effector of the rope. Now, each and every joint is being attached with the help of a link, right? Each and every joint is being attached with the help of the link to the end effector. Now, for the joint 1, we take the constraint as ji minus 1, right? Or j joint I minus 1, and for the link of link 1, we take the term as L I minus 1, right? L I minus 1. This is the second joint where it is Ji, and this will be Li, right? Where it is moving at an angle of theta I, where the joint, when it is taking some particular kinematic movement or it is taking any particular motion analysis, it rotates at an angle of theta I, right? Where the axis is being moved, that is the x-axis, y-axis and z-axis also will be having some movement where it will be taking a direction of xi minus 1 or zi minus 1 or yi minus 1 accordingly. And from one axis to the other axis of the end effector, the distance being maintained, the displacement, whatever is being maintained, is being determined by AI, right? Is being determined by AI. That is, the distance from the axis of the joint to the end effector will be determined by the term AI, where the end effector movement will be given as alpha I, right? Where the end effector movement, angle movement will be determined by alpha I, right? And at the end of the end effector, the joint is being written as Ji plus 1. At the initial position, it is Ji minus 1, and at the end position, it is Ji plus 1. Right? So here, how do we determine these particular terms for the DH parameter? So here, the term D here in this particular figure is known as the offset. Right? It is known as the offset along the z-axis. Right? It is known as the offset along the previous z-axis to the common normal, where theta is being the angle which is moving from one position to the other position for the axis of z. Right? Where theta is the angle about the previous z from the odd x to the new x, whereas r is nothing but the length of the common normal, right? R is the length of the common normal, and alpha is the angle about the common normal. That is, at the end effector we have an angle alpha. This R is nothing but the AI, which is known as the distance, length of the link, and theta is the angle which has been obtained at the first initial joint, right? So how do we find these parameters? What are the constraints to find these particular parameters? That is, initially we need to set the z-axis direction, whether it is in the prismatic axis or whether it is in the form of a rotational axis, right? We will be setting the z-axis direction, which is the actuator rotation, or it is in the prismatic axis rotation. Nextly, we will go for a rotational axis, deciding where the theta angle will be placed. That is generally for a rotational axis. So here we have two types of axes which we consider. That is, one is prismatic and one is the rotational. So here what happens in this particular two axis direction? What do we mean prismatic? Prismatic is nothing but the axis which is rotating in the vertical direction, up and down, and also in the rotational direction. Whereas the rotational direction takes place only in the rotational axis, that is in this particular form. For example, we have a cylinder and here we have some robot link being placed. In the prismatic direction, this particular link will be moving up and down of the axis, whereas this will be moving only in the rotational direction. That is known as prismatic and rotational axis. So coming to the y-axis, we will be finding out the right hand rule and the perpendicular to the z and x-axis in order to find out the parameters. Finally, we find the displacement of the axis. So here, the DH convention, we need to find out the DH convention, that is at what angle, how that particular axis is being rotating. So initially we take AI. AI is nothing but the displacement of your particular axis, right? So here this particular conventional link is being related with the homogeneous transformation, right? So the Denavit and Hartenberg convention is being linked up with the help of the homogeneous transformation, where AI will follow four particular basic rules, and these are the four basic rules with respect to the forward kinematics. With respect to the forward kinematics, in order to get the DH conversion with the help of the homogeneous transformation, we need to find out these particular four basic rules. One is rotation at the angle theta about the axis z, and the next one is translation along the z axis for a value of di, and the next is rotation of the x for an angle alpha I, that is near the end effector, and the fourth one is the translation along the x-axis for the value of ai. This is also again near the end effectors. So how do you determine this particular ai? How do you find out this particular ai transformation matrix? So that is equal to rotation of the z comma theta I, that is the angle theta with respect to the z-axis, into di with respect to the translation of the x-axis, into the rotation of the x, rotation of the angle alpha I with respect to the x-axis, and next is the translation along x for the value, where ai is called as the link length, right? AI is called as the link length, alpha I is called as the link twist, DI is called as the link offset, and theta I is called as the joint angle. Right? Now, based upon these particular four constraints, we will be finding out the matrix for AI. So, how do we find out the matrix for AI here? Into here we need to write one more term, into translation of x comma AI. Right? So how do we find out this particular transformation matrix with respect to this particular term, where AI is known as the length of the link, alpha is the twist, the angle for twist for that particular link, and di is the link offset, and theta is the joint angle. That is here whatever angle is being formed theta, this is known as the joint angle. So how do we write the matrix for this particular AI now? AI is equal to cos theta I minus sin theta I 0 0 sin theta I cos theta I 0 0 0 0 1 0 0 0 0 1, right, into 0 0 0 0 1, right, into AI 0 1 0 0 0 0 0 into the matrix 1 0 0 0 0 cos alpha I 1. So in this particular form, we write the uh, um, transformation matrix. So for the transformation matrix of the AI, we are getting this cos angle with respect to this particular figure. So when we are considering the rotational matrix for an angle theta at an z axis, we will be getting cos theta I minus sin theta I, and at the z axis it is 0 and 0. That is, here we write the matrix in this particular form. That is, we are taking the rotational matrix and we are taking a prismatic matrix. So rotational matrix, we will be getting these constraints and this will become 1 here, right? And here we will be getting 0 0 0 and 1, and remaining will be a homogeneous transformation matrix. That is cos theta I minus sin theta I 0 0, which because it is 0 at the prismatic, and sin theta I cos theta I 0 0. This is for the first rotation matrix, that is for an angle theta at z axis, right? This is the translation matrix, this is again the translation matrix, and this is the rotational matrix at an angle alpha, right? This is again the rotational matrix at an angle alpha. So this is the matrix which we will be acquiring. And finally, the final DH matrix will be, so I hope you have taken down this. And the final DH matrix, we, with respect to this matrices, we will be writing it as the final DH matrix will be written as cos theta I minus sin theta I and cos alpha I sin theta I sin alpha I into AI cos theta I. This sin theta I cos theta I and cos alpha I minus cos theta I sin alpha I AI sin theta I 0 sin alpha I cos alpha I di 0 0 0 and 1. So this is called as the final homogeneous transformation matrix for AI. Right, this is finally called as the homogeneous transformation matrix for AI, which is also called as the Denavit Hartenberg matrix. Right, Denavit Hartenberg matrix with respect to the translation and rotation of the axis. Now, let us take an example. Let us take an example of a planar elbow manipulator. Now let us take an example of a planar elbow manipulator. Now for this particular planar elbow manipulator, how do we write the matrix with respect to the DH parameter? Right, now let us example of a planar elbow manipulator. Now for this, how do we write? We are having axis where this is one of the link and this is one link which is moving at an angle theta 1, having a distance ai, right, and this distance is a2 extended. This is at an angle theta 2 y-axis and x-axis, right, where this is nothing but the y-axis. Right. So how do we write the matrix for this particular example? That is, when we take any particular planar elbow manipulator which is moving at an angle theta 1 and theta 2 with respect to two joints at a distance of a1 and a2. How do we write the matrix for this particular term? How do we find out? First, we need to draw table, that is link. What is the AI distance? What is the alpha I? What is DI? And what is theta I? Right? Now, for link 1 and link 2, what is AI? It is nothing but A1 and A2. That is the distance from joint 1 to joint 2. What is AI? What is the distance? What is the length of this particular link? It is nothing but A1. And for link 2, what is the length? It is nothing but A2. And what is alpha I? Here we don't have end effector, so it is we are considering it as 0. And here we don't have any sort of offset for this particular planar elbow. We are considering it as 0. Whereas theta I is nothing but theta 1 and theta 2. Now, how do we find out the AI matrix for this particular transformation? Okay, so this is all for today. We'll continue it in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.